Hi, I'm Mark Barsamian with the Ohio University Math Department. In the previous video, I discussed metric geometries. These are geometries in which there's a distance function and in which every line has a ruler. In the current video, I'll be discussing rulers some more. I'll be discussing how to get new rulers from an existing ruler on a line, and I'll be discussing rulers that have a certain kind of special property that's often desirable. This video is produced for Ohio University Math 3110-5110 College Geometry. The reading for this video is from section 2.3, Special Coordinate Systems, in the book Geometry, A Metric Approach with Models by Millman Parker. The corresponding homework is this collection of 6 exercises from section 2.3. Recall some stuff from previous sections of the book, previous videos. The definitions of surjective and injective functions from way back in chapter 1. A function is called surjective if it has this property. For every element in the range of the function, there exists an element of the domain, at least one, that can be used as input to cause that desired element of the range to be output. And the definition of an injective function is this. If two inputs cause outputs that are equal, then the inputs must be equal. Recall some more recent things from section 2.1, the definition of abstract geometry and the definition of incidence geometry. The procedure for finding the Cartesian line passing through two distinct points in R2. And the procedure for finding the Poincare line passing through two distinct points in the upper half plane. And some important things from section 2.2, the definition of a distance function, and the definition of the Euclidean distance function on R2, and the taxicab distance function on R2. The Euclidean distance function is the old familiar distance function. The taxicab distance function is this very different looking thing. And recall the definition of the Poincare distance function on the upper half plane. It is this very messy formula in the case of points that don't have the same x-coordinate, and it's this slightly better looking formula in the case of 2 points that do have the same x-coordinate. And remember that to find the distance between 2 points in the upper half plane in the Poincare distance formula, you have to know the center and the radius of the semicircular line that those points lie on. So you need to find these constants C and R. And recall the definition of a ruler for a line. A ruler for a line is a function from the line to the real numbers. That is, it eats as input points that are on the line and spits out as output real numbers. And it has to satisfy these requirements. The function must be a bijection, and it must agree with the distance function in the following way. If you have 2 points on a line, P and Q, not necessarily distinct, then if you do this, if you take P and you feed it into the function f to get a real number, and you take the point Q and you feed it into the function f to get a real number. You take the difference of those two real numbers and you find the absolute value of that difference, you get a number. That number has to equal the number that you would get by just measuring the distance between P and Q. Remember that you can talk about rulers only in a metric geometry, and in that setting you have a distance function. So you have one function called f, that's a ruler for a line L, and you have this other function that's the function d, that's the distance function for the geometry. This equation is called the ruler equation. The number f of p is called the coordinate of p with respect to f. Now recall the definition of a metric geometry. A metric geometry is an ordered triple of 3 things: a set of points, a set of lines, and a distance function that satisfies this list of requirements. The set of points in the set of lines is qualified to be called an incidence geometry, and D is qualified to be called a distance function on the set of points, and the triple has to satisfy this third requirement that every line has a ruler. In other words, every line has one of those special functions that satisfies the requirements to be called a ruler function. This requirement is called the Ruler Postulate. And recall our examples of metric geometries. This triple, consisting of the Cartesian plane incidence geometry along with the Euclidean distance function, that triple is called the Euclidean plane. So the Cartesian plane, points and lines, with the Euclidean distance function gives you the Euclidean plane. This triple, consisting of the same Cartesian plane again, but with the taxicab distance function, this satisfies the Ruler Postulate, and so this triple is qualified to be called a metric geometry as well. That's called the taxicab plane. So remember that both the Euclidean plane and the taxicab plane have as their underlying set of points and lines the Cartesian plane. The only difference is the Euclidean plane has the Euclidean distance function, whereas the taxicab plane has the taxicab distance function. Another example that we studied was this triple, consisting of the Poincare plane along with the Poincare distance function. And that triple is called the Poincare plane metric geometry. So that notation is a little bit confusing. We call this the Poincare plane, and we call this the Poincare plane. We call the incidence geometry the Poincare plane, and we use the same name for the metric geometry. Now, since each of these things is a metric geometry, we know that in these geometries, every line has a ruler. In the previous video, we discussed this table of some standard rulers for the various kinds of lines in these metric geometries. So for instance, in the Euclidean plane, for a vertical line, the standard ruler is that function. For a non-vertical line, the standard ruler is that function, and so forth. Now, before going on with material from section 2.3, I want to discuss a previously overlooked definition when we were discussing abstract geometry and incidence geometry. Recall that in an abstract geometry, for every two distinct points, A and B in the set of points, there exists at least one line in the set of lines that both those points lie on. For two particular distinct points, A and B, it's possible that there's more than one line that they both lie on. We saw examples of this. In this abstract geometry, the 2 points B and D both lie on this green line, that is this set, and they also both lie on this red line corresponding to that set. So in abstract geometries in general, we cannot say this phrase, the line that B and D both lie on, because that phrase is ambiguous. In this particular geometry, there are two lines that B and D both lie on. So more information would be needed to specify which line is being referred to. So you can't say the line that B and D both lie on in general, because you don't know if there might be more than one. But in an incidence geometry, for any two distinct points, there's exactly one line that both points lie on. For instance, in this incidence geometry, which is similar to the abstract geometry from the previous page, we can use this phrase, the line that B and D both lie on, because there's only one line, that line. There's no ambiguity when I say these words. So that's the idea behind this notation. It's the notation for the unique line containing two given points. The symbol is this. You put two letters with a double arrow above them, and this is spoken line AB. Now you only get to use this symbol when you have an incidence geometry in the discussion, and A and B are in the set of points for that incidence geometry. And what that symbol means is the unique line that both A and B lie on. So this is a symbol that we get to use in instance geometry. We can't use that in an abstract geometry. Now I want to discuss material from section 2.3. The first topic is getting new rulers from old rulers. I'll start by discussing the way we measure distance in a drawing. In a drawing, given a ruler lying along a line, so for instance here could be your line L, and you could have a ruler. Now I'm going to draw the ruler that way. That's meant to be a ruler with the 0 where it's shown and then the positive numbers going off to the right. There are two simple operations that can be done to obtain a new ruler. One is that you can slide the ruler along the line. So there I've just slid that same physical ruler along the line. So I'll call that sliding. There's another operation that you can do. You can keep the 0 of the ruler pinned to its current point on the line. So I didn't mark the initial position of the 0, but you can imagine if there were a green point on that line up there, then that green point is there now. So another operation you can do with a ruler in a drawing is you can keep the 0 of the ruler pinned to its current point, but flip the ruler so it points in the other direction. So now the ruler is pointing in the other direction, but I kept the 0 in the same place, pinned to that green point. Well, in a metric geometry, a geometry that has a distance function in which every line has a ruler, we have analogous operations that can be done on a given ruler, that's a given ruler function, to obtain a new ruler, that is a new ruler function. The sliding operation can be articulated by this ruler sliding theorem. So given a metric geometry, given a line, and given a ruler f for that line, and given any number a, any real number a, the claim is this new function called g that's defined this way, g of p equals f of p minus a, there's that real number a, that function defined that way qualifies to be called a ruler for line L. So this new ruler G is analogous to the ruler that you would get by sliding a ruler along a line in a drawing. Let's prove this theorem. We have to show that this G that I defined in the previous page fulfills the requirements of a ruler for line L. So G is defined this way. Well, what are the requirements of a ruler? Let's go back up and look at the definition of ruler. A ruler for a line is a function with domain the line, that is the set of points that's the line, and the range is the set of real numbers, and it has to have these properties. The function has to be a bijection, that is, it's got to be surjective and injective, and the function f has to agree with the distance function in the sense that it obeys this ruler equation. So we have a candidate, this function g, that was introduced here, and we have to show that it fulfills all the requirements to be qualified to be called a ruler for the line L. So we have to show that g is indeed a function with domain L and range the real numbers. That's one of the requirements for the g to be a ruler for line L. Another requirement is we have to prove that g is surjective. Another requirement is we'll have to prove that g is injective. Another requirement is we'll have to prove that g satisfies the ruler equation. Once we've done all that, then we can that will be our proof. Our proof will be complete. So let's go back and look at the details of this. The first part is easy. We have to prove that g is indeed a function with domain L and range the set of real numbers. Well, that just means that we have to show that this thing called g really does eat points as input and spit out real numbers as output. Well, what happens when you feed G a point? Well, you denote it like that. Well, the way that G is defined is this. To compute G of Q, you do this. Well, the f of Q is a real number, and the number A is a real number. Why do we know that f of Q is a real number? Well, it's because f is known to be a ruler for the line. So f of Q is going to be a real number. And when you subtract two real numbers, you get a real number. So this quantity will be a real number. So this simple looking equation shows that G is a function with domain L and range R. So this first part of the proof is so deceptively easy, but it's very important to do this kind of thing. Mathematicians do this and call this proving that the function is well defined. That is, it really does qualify to be called a function. Now, what about proof part 2? How do we prove that G is surjective? Remember what it means to say that a function is surjective. For every element of the range, there exists an element of the domain that can be used as input to cause that element of the range to be output. In our current situation, we have a function G, and the domain is the set of points on line L, and the range is the set of real numbers. So what we're going to have to show is this. For every real number t, there exists a point, I should say a point P on line L, at least one, such that this is true. So how will this be incorporated into the proof structure? Well, we want to end by saying that G is surjective, and so we'll start by saying, suppose that there is some real number t, and we have to end by saying we found a point P on the line such that G of t equals P. And so these two things together will allow us to end the proof by saying that G is surjective. So we have no choice about how this proof has to end. It has to end by us saying G is surjective, and we have no choice about the proof structure that'll get us there. We have to start with this, and we have to end with this right before that blue statement that's going to end the proof. So now our gap is here. This is one of those proofs where the mysterious middle of the proof is a little bit mysterious. How do we get from that red statement to that green statement? Well, the middle of this is kind of a trick. Think about the fact that we're supposing that we've got some given real number t. Well, since t is a real number, we know that t plus a is a real number as well. And since f is known to be surjective, we know that there's a point P such that f of P equals that number, t plus a. So f of P equals t plus a. Now, that means that when we compute G of P, well, G of P equals f of P minus a. But f of P, we can substitute in that quantity. And so we end up with this tricky little operation here. T plus a minus a equals t. I'm not sure if that explanation really helps. So just study this proof very carefully. Notice the structure, starting with suppose t is a real number. Come up with an example of a point P on the line such that G of P equals t, and that's how you're allowed to say that G is surjective. Now, notice one thing before we go on. The proof that G is surjective had at its heart this fact, the fact that we knew that F is surjective. And that was because we know that F is a ruler. So proving that G is qualified to be called a ruler is going to involve using the fact that we know that F is a ruler. Now what about proof part 3, proof that G is injective? Well, how do we prove that? Remember what it means to say that a function is injective. If two inputs cause outputs that are equal, then the inputs must be equal. Well, so in our current situation, our function g is a function from the line L to the real numbers. So what we have to prove is this. If we have 2 points on the line L such that g of p equals g of q, that is, if they cause outputs that are equal, then those points must have been equal. So we'll do a direct proof. So we take that hypothesis, and that goes in our first line. Suppose we have 2 points on the line that cause outputs that are equal. Then we have to get to here. We have to prove that P must have been equal to Q. And that's what will allow us to say that G is injective. These two statements are the frame of the proof that G is injective. So how do we get from here to here? How do we bridge this gap? Well, this is not so mysterious. In this case, we have this statement to say that G of P equals G of Q. Well, that's a defined term. So we have no choice about what to do next. We have to unpack that definition. To say that G of P equals G of Q really means this. This quantity equals that quantity. So we unpacked the definition. Now we can use some arithmetic. We end up with this equation, f of p equals f of q. Well, if we know that f of p equals f of q, we're allowed to say that p equals q, because we know that f is injective, because f is a ruler. And so look, we got to where we needed to go. Our goal was to prove that p must equal q, and we got there. So therefore, we can say that G is injective. Finally, how do we prove part 4, that G satisfies the ruler equation? Well, remember, the ruler equation has on its left side this expression, and on its right side this expression. Well, let's start by building the left side and see where we can go. So we start by building this. Now for the first equal sign, we just use the definition of G. And then for the second equal sign, we just used arithmetic. And then for the third equal sign, we just used the fact that f is a ruler. So f satisfies the ruler equation. So we end up with a long string of equalities that can be wheezed together to give us the equation that we wanted. This green expression equals this red expression. That's the end of the proof of the ruler sliding theorem. Now there's another theorem about behavior of rulers in a metric geometry that's analogous to the flipping of a ruler in a drawing. This theorem is called the ruler flipping theorem. It says this: if you're given a metric geometry, and you're given a line, and you're given a ruler for a line, here there's a typo, this shouldn't be here. If you're given these things, the claim is the following. If you define a function g this way, g of p equals the negative of f of p, then that function g qualifies to be called a ruler for line L. Now this new ruler g is analogous to the ruler that you would get by flipping the direction of a ruler on a line L in a drawing. Now I won't prove the ruler flipping theorem. I'll just remind you though that the outline will be the same as the outline for the proof of the ruler sliding theorem. See if you can provide the details for this proof. You'll have to prove that g is indeed a function with domain L and range R. You'll have to prove that g is surjective. You'll have to prove that g is injective. And you'll have to prove that g satisfies the ruler equation. Now I want to talk about combining ruler sliding and flipping. The previous two theorems, the ruler sliding theorem and the ruler flipping theorem, can be used to prove this theorem that's presented in the book. It's theorem 2.3.1. I call it the ruler sliding and flipping theorem. So you're given a metric geometry, you're given a line L, you're given a ruler for that line, given any number A, that's a real number, and you're given a number epsilon that's either 1 or -1. The claim is this thing, this weird-looking thing, well, this is a function. This symbol h with a subscript a and a subscript epsilon just means that you're going to use this number a and this number epsilon in the formula for this function h that you're going to define. So here's how the function h with a subscript a and a subscript epsilon is defined. The function, when you feed it a p as input, here's how you compute the output. First, you compute f of p using that given ruler. Then you subtract the value of a, and then you multiply that whole quantity by that number epsilon. So just some arithmetic steps. So the claim is this wacky function that's defined this way qualifies to be called a ruler for that line L. Now, a remark about this new ruler that we've defined is analogous to the ruler that you would obtain by sliding a ruler along a line in a drawing and then flipping the ruler, flipping it if epsilon equals -1. So I'm going to sort of sketch a proof of the ruler sliding and flipping theorem. So suppose all that given stuff is given. You have a metric geometry, a given line L, a given ruler for line L, a number a, and another number epsilon that's either 1 or -1. Well, there are two cases. Remember that epsilon is either 1 or -1, so that's an or statement. We have this or statement in the given information. Well, that is a hint that maybe we should use a proof by cases. So the first case is when you suppose epsilon is 1, well then the formula for h is simpler. Epsilon is 1, so you put a 1 here. Well, then the formula for h of p, is that thing. Well, that's qualified to be called a ruler because that showed up earlier in the ruler sliding theorem. If we have a given function f of p that's a ruler, and we build a new function by doing this, then that new function that we've built is qualified to be called a ruler. So in this case, the claim is true. Case 2 is, suppose that epsilon is -1. Well, this case is just one step longer. We're going to start by letting g be this function, the function that's defined this way. Well, that function is qualified to be called a ruler by the ruler sliding theorem. And then look at the function h. The function h has a -1 in front of that stuff. In other words, it's just the negative of g. Well, the ruler flipping theorem says if you have an existing ruler and you create a new function by putting a negative sign in front of it, then the new function that you've built is qualified to be called a ruler. That's the ruler flipping theorem. So that means that this new function that we've built is qualified to be called a ruler. So the claim is true in this case as well. So the conclusion of cases is, well, this function that we build is qualified to be called a ruler because it's true in both cases. Now I want to talk about special rulers and the ruler placement theorem. In a drawing, when you're using a ruler to measure the distance between two given drawn points, A and B, it's most convenient to put the 0 of the ruler on one of the points with the ruler oriented so it goes in the direction of the other point. So for instance, if this is my line, and I have a point A, and I have a point B, then the most convenient orientation for the ruler would be this. Put the 0 on A, and the positive end of the ruler pointing towards B, and then whatever number is on the ruler right next to B, that's going to be the distance between A and B. Well, in axiomatic geometry, where rulers are functions, it's similarly often convenient to have a ruler that behaves in an analogous fashion. That's the idea behind what's called the ruler placement theorem. Typo here. The ruler placement theorem says this: given a metric geometry and any two distinct points, claim is there exists a ruler G for that line AB that has these properties: G of A equals 0 and G of B is positive. We call this kind of ruler a ruler with A as origin and B positive. In other words, the analog to this kind of ruler in a drawing. I won't discuss the proof of the ruler placement theorem because there's a nice proof in the book, but I will point out that the steps in the book's proof provide us with a procedure for finding a ruler with A as origin and B positive for any two given distinct points in a metric geometry. I'll present the procedure here. So here's the procedure for finding a ruler with A as origin and B positive for distinct points A and B in a metric geometry. So in other words, the procedure for finding one of those special rulers. Suppose you're given any two distinct points. Then start by letting F be a ruler for the line AB. We know a ruler exists because M is a metric geometry. In a metric geometry, every line has a ruler. So we know that we can do this. We can just say, grab a ruler for line AB. Now we can use F to obtain a new ruler in the following way. We're going to define a real number epsilon by this. Epsilon is the sign of the quantity f of b minus f of a. In other words, if f of b minus f of a is greater than 0, then the sign of it is plus 1. On the other hand, if f of b minus f of a is less than 0, that is, if it's negative, then its sign is negative 1. Now we're going to define a function. That's going to be its symbol. H is the name of the function, and then it has as its subscripts an f of a and this number epsilon. Now this is going to be a function from line AB to the real numbers. So if I'm going to sell you a function, I have to tell you what it does when you feed it a point. So if you take this function and you feed it a point P, how does the function produce its output? Well, you take that point P and you feed it into F to get f of P. And then you subtract from that f of A, and then you multiply that difference by this number epsilon. Whatever you got for your epsilon up here is sitting right there. Well, when you build a function that way, this is going to be a ruler with A as origin and B positive. Now this notation is excruciating, so I'm going to just jump right in and do some examples where we build this kind of thing. And you'll see that this function notation, although it's very, very messy, it's actually descriptive and really gives you the complete instructions for how to build a special ruler. So for example 1, in the Euclidean plane, let A be 4, 3, let B be 4, 2, and let C be negative 4, 5. So question A is, find a ruler with A as the origin and B positive. We'll notice that the x-coordinates of A and B are the same. So A and B lie on a vertical line, this line L subscript 4. So line AB is that vertical line. Now remember our procedure. We are hoping to build a special ruler. We have to start by getting a ruler for line AB. Well, how are we going to get a ruler for that line? Well, remember that we do have a source for rulers. We know that there are some standard rulers. For the vertical line L subscript A in the Euclidean plane, the standard ruler is f of a comma y equals y. So there's the ruler that we'll start with. So the standard ruler for that line is this function, f of xy equals y. Now that we've got that standard ruler, what are we supposed to do? Well, we have to find the value of epsilon. We have to figure out whether epsilon is +1 or -1. To do that, we have to find f of b minus f of a and figure out whether it's positive or negative. Okay, well, here's our standard ruler. We use that to find f of a, we get the number 3. We use that to find f of b, we get the number 2. So when we compute the difference, f of b minus f of a, we get 2 minus 3, so we get the number -1. That's a negative number. So therefore, we declare that epsilon is -1. Not because this is -1, but just because this is negative. Epsilon gets defined to be -1 whenever f of b minus f of a is negative. So we've got our value of epsilon. We already know our value of f of a. So now we're going to define g by just building this. So that means that we have to park our epsilon in front of this expression. Well, our epsilon is that number -1. Now our function f of xy, that's just y. So a y goes here. And then our f of a, well, we've got that sitting here. That's the number 3, so that goes here. So we just build this. We have minus parentheses y minus 3. In other words, we've built a function g of xy with this formula. G of xy equals 3 minus y. Then this thing that we've just built is a ruler with a as origin and b positive. Let's check. Let's compute g of a. Well, g of a, that's the point a is 4, 3. That means that we put 4, 3 inside the formula for g. Now, g does this. There's the formula for g, and I grab whatever's sitting here, and I put it here. And so the result is g of a is equal to 0. And that's what I wanted. G of a has to be 0. Now let's see what g of b is. For g of b, I grab the coordinates for point B and I put them inside of g. Now I use the formula for g. Here's the formula for g, but I use the y coordinate of this point in that spot, and I get the number 1 as the result. And notice that's positive. That's what I wanted. So g of a is equal to 0, and g of b is positive, and we know that the function defined this way qualifies to be called a ruler function. So we have one of those special rulers we've built. So that's our first example of using this procedure to find a special ruler. Example 1, question B. Find a ruler with a as the origin and c positive. So remember, a is 4, 3. C is -4, 5. Well, since those 2 points have different x coordinates, we know that this line, AC, is a non-vertical line. L subscript m, b. Now, to find the standard ruler for that line, well, what is the formula for the standard ruler for a non-vertical line? For a non-vertical line, the formula for the standard ruler is that f of xy equals x times the square root of 1 plus m squared. So we need to find the value of m for that line in order to build this standard ruler. So we need to find the value of m for the line containing a and c. So we do change in y over change in x for those 2 points, and we get the number -1/4. So that's our slope m. We use that to build the standard ruler, and we end up with this. The standard ruler is f of xy equals x squared of 17 over 4. Now what's next? We found our standard ruler. Remember what we have to do next. We have to figure out the value of epsilon by looking at the sign of the difference, f of b minus f of a. So we need to compute f of b, compute f of a, compute their difference and figure out the sign of that and use that to decide whether epsilon is positive or negative. Well, with this standard ruler and the point A that we're given, A is the point whose coordinates are 4, 3. When we compute f of A, we use this formula, and we use the value of 4 in that formula for x, and we end up with f of A equals square root of 17. Now we have to compute f of c. Well, c has these coordinates, negative 4, 5. So when I use the standard ruler and I use that coordinate for x, I get that f of c is this number, negative square root of 17. So therefore, this quantity, f of c minus f of a, will be negative. And so we use the value negative 1 for epsilon. So we have a value for f of a. F of a is that number, square root of 17. And we have a value for epsilon. Epsilon is the number negative 1. Now what do? We have to build a function by doing this. The function called h will do this when it receives a point p as input. The point p will be fed into f to get f of p, and then we'll subtract that value of f of a that we computed. We'll take the difference, and we'll multiply that difference by our value of epsilon. So we have to build one of these things. So we have our f of a is there, and our epsilon is there. And we're going to build our function g this way. We put the epsilon out front, we put our f of a here, and then our f of xy is there. So our epsilon is this negative 1, our f of a is this number square root of 17, and then there's the formula for our standard ruler. That's what f of xy is. It's this formula from the standard ruler. And this whole thing is a new formula for a new function that's called g. Well, when I simplify this, I get this, that g of xy is that mess. Square root of 17 minus x square root of 17 over 4. And the point of this is that g, this new thing, is a ruler. And it's a special ruler. It has a as origin and it has c positive. Now let's check that it really qualifies to be called a special ruler. Let's check to see what a g of a is. Well, we have to feed in the coordinates of a. Now the only place in here where there's a room for a variable is this spot here. So we take this whole formula and we bring it down here, and in that spot we put our x coordinate, which is the number 4. So when I do that, we end up with the number 0. Now let's see what g of c is. We put the coordinates in for point c. We bring down this whole formula. The only place where there's room for a variable is this spot. I put the x coordinate there, and I end up with the result of 2 square root of 17. All we care about is that that's supposed to be positive, and it is. So both requirements are satisfied. Let's go on. Example 2. In the taxicab plane, we're going to consider those same 3 points. The goal is to find special rulers in the taxicab plane for these same points. Well, so in question A, we're going to find a ruler with A as origin and B positive. Well, just as in example 1, the line that passes through A and B is a vertical line with x coordinate 4. And the standard ruler for that line in the taxicab plane is this, which is the same as the standard ruler for that line in the Euclidean plane. So all the work we did in example 1a is going to be recycled for example 2a. The result is we get this new ruler, g of xy equals 3 minus y. The same exact function that we came up with in example 1a. Example 2 part B. Find a ruler with A as origin and C positive This is in the taxicab plane. Well, just as in example 1b, line AC is a non-vertical line with slope m equals -1/4. Now remember that the taxicab plane has the same underlying incidence geometry as the Euclidean plane. That is, the underlying incidence geometry is the Cartesian plane, the set of points and lines. And so line AC was this non-vertical line with slope m equals -1/4 in example 1b, and it's going to be the same in example 2b. We're in the taxicab plane now, but the lines are the same lines. What's different is the standard ruler for that line in the taxicab plane is this thing. That's a new function. In the Euclidean plane, the standard ruler for that non-vertical line was that thing, x times square root of 1 plus m squared. In the taxicab plane, the standard ruler is f of xy equals x times the quantity 1 plus absolute value of m. Well, we know what m is. M is this number, -1/4, so we put that in, and we end up with this formula. The standard ruler is f of xy equals x times 5/4. Now, what's next? Remember, once we've got a ruler, we have to figure out the value of epsilon by looking at the sign of f of b minus f of a. Well, now here it all starts to be very familiar. This is very much like the example 1b, so I'm going to let you read this. The result, though, is that the ruler that we end up with is this. For the taxicab plane, the special ruler for points A and C, the ruler that has A as origin and C positive, is this formula. So a different formula than the formula for the special ruler in the Euclidean plane. Let's go on. Example 3. In the Poincare plane, we're going to consider those same 3 points. We're going to find a special ruler with A as the origin and B positive. And then in question B, we're going to find a special ruler with A as origin and C positive. Well, we start by figuring out what kind of line A and B lie on. Since A and B have the same x coordinate, we know that line AB is a type 1 line, denoted by this symbol. So what do? We have to start by coming up with a ruler, kind of a starting ruler. So remember that we start with the standard rulers from that table. The standard ruler for a type 1 line in the Poincare geometry is this: f of xy equals ln of y. So that's our starting ruler. Now what do? Well, remember, once we have a starting ruler, we have to figure out the value of epsilon. So to do that, we find out what f of a is, and we find out what f of b is, and we subtract. Well, it turns out that in this case, f of b minus f of a is negative. I'll let you go through the steps in detail. So since f of b minus f of a is negative, that tells us that we have to choose epsilon to be -1. So now we are going to use our value of f of a that we got. Remember that we found out that f of a was ln of 3, and we've figured out that epsilon is -1. So we're going to build a function, g of xy, and here's how we're going to do it. We're going to take f of xy. F of xy is ln of y. We're going to put it there. So there's my ln of y. And then we're going to subtract our f of a. Well, f of a, I didn't do very good color coordinating, did I? F of a is ln of 3, so that goes there. And then I park our epsilon in front of that expression. So what we've built is a function that's this: g of xy equals ln of 3 minus ln of y. Now, that's qualified to be a ruler because of that ruler sliding and flipping theorem, and it's a special ruler. It's a ruler with A as origin and B positive by that ruler placement theorem. But let's check. Let's check to see that it really is a ruler that has those properties. Well, let's compute G of A. So that means we bring this formula over here, and the only place for a variable in that formula is this spot. I take my y coordinate of my point and I put it in that spot. Well, when I do that, I get the number 0. That's good because G of A, we want it to be 0. Now let's compute G of B. We bring this formula down. The only place for a variable in this formula is here. Now that should be a 2. There's a typo. And we end up getting this result, ln of 3/2. Now all we cared about was we wanted G of B to be positive, and it is, because 3/2 is greater than 1, so when I take its logarithm, I'll get a number that's greater than 1. Let's go on. Example B. Find a ruler with A as origin and C positive. Well, we start by figuring out what kind of line AC is. Well, because the x-coordinates of A and C are not the same, remember the x-coordinate of A is the number 4, and the x-coordinate of C is the number -4. Since those are not the same x value, we know that that line AC is a type 2 line. Well, we need to have a starting ruler for the line, and the only place we can come up with a ruler is that table of standard rulers. Now remember, to build the standard ruler for the line, we have to build this. That formula has the C and the R in it for the line. So we have to figure out those values. We compute the value of C by just plugging in to that formula from section 2.1, the formula that gives you the value of C. That formula is put for reference at the start of the notes for this video. We end up with the value C equals -1. So that's the x-coordinate of the center of that semicircular shaped type 2 line that points A and C lie on. And then we use that value of C in this computation to find the value of R. Now this computation is kind of unfortunate. It comes out to be an ugly number, square root of 34. So we have a value of C equals 1 and a value of R equals square root of 34. So we just simply use those numbers to build that formula for the standard ruler. We simplify it a little bit and we end up with this. F of xy equals that. Now what's next? We have to figure out if epsilon is going to be +1 or -1. To do that, we've got to figure out whether f of c minus f of a is positive or negative. We just grind it out. We compute f of a by taking the coordinates for point A and putting them into this formula. The only place for variables in this formula is here. The x goes there, and the y goes here, and we end up with this horrible looking thing, which we can just type into a calculator to get an approximate decimal for. It's roughly 1.284. We do an analogous thing for f of c, and we get that f of c is roughly minus 0.569. So in other words, f of c minus f of a will be negative. So remember what we do with that information. All that work was just to figure out the value of epsilon. So look, now we have the value of epsilon, and we have the value of f of a. F of a is this mess. So we use that value of f of a, and we use that value of epsilon to build the formula for our new ruler function. So we do the same thing we've always done. We take our formula for f of xy and we put it there. We take whatever value we got for f of a and we put it there. and then we multiply the difference of those two things by that value of epsilon, whatever we got. Well, so there's a value of epsilon. There's our formula for the standard ruler parked there, and there's the expression for that number, f of a, there. That's just a whole bunch of messy stuff. And that can be simplified to this. G of xy equals that mess. The result is that this G is a ruler with A as origin and C positive. So let's check this by computing G of A. So G of 4, 3. Well, we go get our formula for G of xy. That's this big messy formula. Now notice that in that formula, there's only one place for an x, it's there. There's only one place for a y, it's there. So we're going to bring this whole formula down, and it's sitting here. And the one place for the x is there, so that x got put there. And the one place for the y is there, so that y got put there. And look, these expressions are going to cancel. We're going to end up with a result of 0. That's good, because this was supposed to be a special ruler. G of a was supposed to be 0. So good. Now let's compute G of c. Well, the coordinates of c are x equals -4 and y equals 5. We go get that horribly messy expression for G of xy, and we park our value of x there and our value of y there, and we just grind it out. And in the end, we end up with this number for G of c. All we care about is that this is positive. We just wanted this to be a special ruler. But we can actually check this in another way. These numbers are so ugly, it would be nice to have some assurance that we did the right thing. Well, one thing that's cool is, remember the relationship between rulers and the distance. I have a value for G of a. G of a is 0. And I have a value for G of c. G of c is this number. Well, if I compute G of a minus G of c, and I take the absolute value, what I've computed is the distance between a and c. That's the cool thing about rulers, about ruler functions. You do this calculation, and that's a way to get the distance. Well, that distance, when I use G of a is 0 and G of c is this number, I figure out that the distance between a and c is roughly 1.83. Now, it doesn't matter which ruler you use. Earlier, we had a standard ruler, and for the standard ruler, f of a was that, and f of c was that. When I subtract those numbers and take the absolute value, I again get 1.853. So again, using the standard ruler to figure out the distance, I figured out that the distance was 1.853. And now using our new special ruler to find the distance, I get the same distance. So that's good. It's a little bit of reassurance that we must have done the right thing. Well, that's the end of this example, and that's the end of the video. Thank you.